Okay, so now let's look at some examples that mixes the different counting types so that you want to keep you a bit honest, so that way you can't cheat. So number one, suppose we have to select 5 managers from a list of 10. How many ways can this be done? Okay, so let's say the managers are A through J. That's your 10 managers. We cannot select the same manager twice. That wouldn't make sense. And there's no repetition. Now, A, B, C, D, E and A, C, B, E, D, even though they're rearranged, represent the same set of managers, so order does not matter. Therefore, this would be a combination problem. 10 managers, how many subsets of 5 can I get out of 10? Now the next one, suppose we have to select a manager, assistant manager, and night manager from a list of 10 people. Well, these assignments change the above problem from a combination to a permutation. So same thing is true about repetition here, but let's say A, B, and C implies A is the manager, B is assistant manager, C is night manager. Well, then if we rearrange the order, then we would get C was manager, A was assistant manager, and B was night manager. So obviously the order is relevant because we're making assignments here. So this would be a permutation problem. Out of 10 managers, how many ways can I assign to the 3 positions? So it'd be 10p3, which is 720. Well, now let's turn to a deck of cards. How many ways can a 3-card hand be selected for standard deck? In other words, how many 3-card hands are possible? Well, there's no repetition because the same person cannot get the 3 of clubs twice. So you can't get, a card twice. So 3 of clubs, 9 of diamonds, 8 of spades is the same hand as 3 of clubs, 8 of spades, 9 of diamonds. So therefore the order is irrelevant. So this would be a combination problem, and there's 52 cards in a deck, and we want to know how many 3-card hands there are. If you want to know how many 5-card hands there are, which is a common way to play poker, you can put a 5 in here for a 3 and see that it's over 2.5 million 5-card hands. Now I kind of changed this number 3 up a little bit, and I said 3 cards are selected randomly and given to 3 different players. How many possibilities exist? Well, this time, if I take the 3 of clubs, 9 of diamonds, and 8 of spades, that would imply one player gets the 3 of clubs, another player gets the 9 of diamonds, another player gets the 8 of spades. But if we rearrange them, then that could mean a whole different assignment. So a different player could get the 3 of clubs and the 9 of diamonds and 8 of spades if I rearrange them. So that means order is relevant. So not irrelevant. Order is relevant. So that would mean this is a permutation problem. 52p3. Okay. So now a card is selected from a standard deck of cards, then put back in, and the deck is shuffled. This is done 3 times. How many 3-card hands can you receive? Well, this time, since I'm putting the card back in each time and we're recording the result when we get it, then repetition is possible. Now, since repetition is possible, that means that we can't use permutations or combinations anymore. Now we have to go back to the multiplication principle. So ask yourself, on the first draw, how many cards are possible? 52. Well, then you put the card back, so that means 52 are possible on the second draw. And then you put the card back, so that means 52 are possible on the third draw. So it's actually 52 cubed, which is 140,608. Number 6 says, a Fiat dealership, a total of 3 cars of a model must be transported to another dealership. If there are 25 cars of this type, how many choices are available for transport? Well, if we numbered the cars 1 to 25, and say we picked car 1, car 15, and car 20, well, that would be sending on the same set as car 15, car 20, and car 1. So order is irrelevant here. Order doesn't matter. So the answer would simply be combination. 25, choose 3, which is 2300. Now, if I wanted to know how many ways I could load the 3 cars on the truck, now that's a different question. By saying I want to know how many ways I can load them on the truck, well, they can be in different places, right? So car 1, car 15, and car 20 is one way to load them. or I could load car 15, car 20, and car 1 in that order. Well, that would be a different order. So now the order is relevant, so this would be a permutation problem of 25 cars P3. And now finally, let's see here. I said at a Fiat dealership, there are 25 cars of a certain model. 15 have automatic transmission, 12 have leather seats, and 10 cars have both automatic transmission and leather seats. How many have either automatic transmission or leather seats? How many have neither automatic transmission or leather seats? Okay, so now what I've done at you is I've thrown at you an addition principle problem. And you should be able to recognize this, because what I've given you here is I've given you a set of automatic transmission, a set of leather seats. So there's like two sets. So you can do a Venn diagram here to answer the questions. Let me see if I can find a little spot to do a Venn diagram. So here is automatic transmission. How about A for that? How about L for leather seats? And we know we've got in the middle, we've got 10 cars that have both. So there's 10 in here. Now remember, there's 15 in this circle, 15 automatic transmission, and there's how many? 12 have leather seats, so there's 12 here. So that means if I take 15 minus 10, there's 5 here that have automatic but no leather seats. And if I take the 12 away from 10, there's 2 here that have leather seats but no automatic transmission. So that's 15, 10, 5, 17 of the 25 cars. So there must be 8 cars that have neither out here. So anyway, let's see now. How many have either one or the other? Well, you could do it two ways. You could add these two together, these three values together, 5, 10, and 2, and get 17. Or you could use the addition principle, because you're looking for the number in the union. So you could say the number in A, which is 15, plus the number in B, which is 12, minus the number in the intersection, which is 10, and that also gives you 17. And then if you want to know how many have neither, then you're looking for these guys out here that are outside the circles. Okay? And that's 8. So that's a Venn diagram problem. Let me get rid of this for you. Okay, now, number 9 says Social Security numbers consist of 9 digits, 0 to 9. If there are no restrictions, how many different Social Security numbers are possible? Well, if there's no restrictions, then repetition is possible. So we have to use the multiplication principle. So I have 10 ways to fill in each number. Okay? So that's going to give me 10 to the 9th possible Social Security numbers. Now, granted, that allows someone with all zeros, someone to have a Social Security number of all zeros. But anyway, that gives me a billion. All right, let's look at number 10. Number 10 says, suppose license plate in one state have 4 letters followed by 2 digits. How many license plate can be created if there are no other restrictions? Well, if there's no other restrictions, then then repetition's allowed. So let's see. Operation 1 would be selecting the letters. And so let's look at that. So to select the letters, if there's no restrictions, there would be 26 times 26 times 26 times 26 ways to choose the letters. And then to choose the numbers, there's 2 digits, so there was 10 ways to choose the first digit, 10 ways to choose the second digit, so that's 100. So I would just multiply these two numbers together and get my answer here, which is over 45 million. The second one said, what if only letters cannot be repeated? So that means that letters cannot be repeated, right? Well, if the letters cannot be repeated, but the digits can, then for the letters, I would have 26 times 25 times 24 times 23, which is 358,800. And since the digits can be repeated, then I would still multiply that by 100. So I'd get a little over, almost 36 million. And then the last one says, what if only digits cannot be repeated? So now the letters go back to this original number, 456,976. And since the digits cannot be repeated, then that would give me 10 times 9 possible digits, which would be 90, and then multiply the two numbers together to get the final answer of about 41 million. Okay, now what's funny about this problem is if you think about it, I always tell students there must be a dirty word committee in the state capitol determining what license plates we must throw out. So regardless of what format you use, there's obviously license plates you wouldn't want to use, like maybe turd 1 or butt 45. I kept it PG, but hopefully you get my point here. All right, now a couple more here. A shipment of 20 disk drives were received from a computer store. 4 of the drives are defective. A sample of 2 are selected randomly. How many different samples can be selected? Well, repetition makes no sense and order doesn't matter, so that would just be 20 choose 2, which is 190. And then it says how many of the samples contain 2 defective drives. Well, the defective drives must be selected from the 4 that are defective, so that means out of the 4 defective drives you want to know how many two sample sets can be selected from the 4 bad drives, so that'd be 4 choose 2, which is 6. And then the third one says suppose one of the samples is tested and one is sold. How many ways can this be done? Well, what that is that's like part A, except it makes it a permutation since you're assigning these to different positions. You're assigning one to be tested and one to be sold. So the order in which they're selected would be important. So therefore this would be a permutation problem, 20P2. Okay, a 5-card hand selected from a deck of cards. How many ways can you get 3 kings and 2 aces? Well, out of 4 kings, you got to choose 3. Out of 4 aces, you got to choose 2. Order doesn't matter, so we're using combinations. But there's 2 operations here, choosing the kings and then choosing the aces. So you have to multiply those answers together to get 24. Exactly 3 4s. Well, to get exactly 3 4s in a 5-card hand, out of the 4 4s, you got to choose 3. And out of the 48 cards that are not 4s, you have to choose 2. And so we have to multiply these 2 operations together to get the total number of hands that would have 3 4s and 2 cards that are not 4s. At least 4 hearts. Well, at least 4 hearts would mean all hands that have 4 hearts or 5 hearts. So first of all, find out how many hands have exactly 4 hearts. So out of 13 hearts, choose 4. And then the 5th card would be out of the 39 non-hearts. So 13 choose 4 times 39 choose 1 gives me 27,885. And then figure out how many hands have exactly 5 hearts. So that would mean out of the 13 hearts choose 5, and out of the 39 other cards choose none, and that's 1287. And then you have to add these 2 numbers together to get the total number of hands that have at least 4 hearts. Okay, so go ahead and read these last 3 problems and make sure that you can answer them, and then you can after you freeze the video you can go back and start the video again. Number 15 is especially interesting, so read that one about the lottery, because you always hear a lot about the lottery and the Powerball. Now, in a moment I'm going to show you some practice problems that I have at the end of this. So you'll have to stop the video on occasions to see those practice problems if you want to see them and see how they're worked. Okay, so here's some practice problems, and I've given you the answers. And you can obviously email me and let me know if for some reason you think I got these answers wrong. So I'll let it sit here for a few seconds, and then I'll scroll it down. And of course you're always welcome to freeze the video if you need to, so that you can have more time to look at the problems. So here we go. So you see 1 through 5 easily there. So let me scroll down to the next group, 6 through 10. And I'll just let the video roll a minute while you take your time and look at those. And again, if you need to, you can freeze the video at this point and then work through these problems. And so that's pretty much the end of the counting techniques. Now make sure you master these counting techniques, because you can't do probability without doing so.